So yesterday, we had derived categories and derived functors in a very general view of derived functors. And today we want to get into some specific derived functors that show up in algebraic geometry, and then we'll start composing them, and Sasha will talk about spectral sequences. And we want to talk about compatibilities among them. So today, derived functors in algebraic geometry. And so we're going to, our abelian category today is going to be, so X is going to be a scheme, probably a Noetherian scheme. And soon it will be smooth and projective over a field before long. And we're going to be interested either in the category of quasi-coherent sheaves on X or the category of coherent sheaves on X. I mean, we're really interested in coherent sheaves, but sometimes you have to talk about quasi-coherent sheaves. So what are our favorite functors? First we have global sections, and this goes from quasi-coherent sheaves on X to abelian groups. And if X is over a field, then it goes to vector spaces. We have Hom between two sheaves. And something to notice is that global sections is the same as homomorphisms from the structure sheaf of X. So to give, if I give you a map from OX to your favorite sheaf, OX has a preferred section, which is the constant function 1. And you just ask where that goes, and it gives you a global section of your sheaf. And you can sit and think about why that's a bijection. That why conversely, given a section, you know there's only one map that sends. Well, if you haven't thought about that, then think about it. Our next one is push forward. So so given f from x to y, a morphism, you have f star from quasi-coherent sheaves on X to quasi-coherent sheaves on Y. And I want you to notice if Y is, well, should I say spec Z? If Y is spec Z, or more often we want to think about just a point, or so spec of a field, then F lower star is global sections. So pushing forward to a point is the same as taking sections. And in general, pushing forward, we'll see, this is often said, but push forward is like taking sections along the fibers of this morphism. Right? You want it to be true that the fiber of the push forward is global sections of the sheaf restricted to the fiber of the map. And it's not really true on the nose, but in some derived sense, it actually becomes true. In general, it's sort of, there's some spectral sequence that compares them, and in the derived category, it's going to become true. Next, let's see. We also have sheaf Hom. So this given, so the local Hom. So given two coherent sheaves you get sheaf Hom between them, and I want you to notice that global sections of sheaf Hom are the same as straight Hom. But if your scheme is affine, for example, then Hom between two R modules is an R module, and so Hom between two quasi-coherent sheaves should be a quasi-coherent sheaf, and then to get global Homs, you take global sections. And then we have tensor product. And we have pullback from quasi-coherent sheaves on Y to quasi-coherent sheaves on X. And these first four are left exact. And the category of quasi-coherent sheaves is, so let me write it. Sections Hom from F to something, push forward, and sheaf Hom from F to something. These are left exact. And the category of quasi-coherent sheaves has enough injectives. Of course, the category of coherent sheaves doesn't, because injectives tend to be really big, and coherent sheaves are sort of not too big. But quasi-coherent sheaves has enough injectives. So we can define, we get the derived, the right derived functors. So from D plus of Q co X to D plus of abelian groups, and so on. And the last two, tensor and pullback, are right exact, and so we get left derived. Well, we'll talk about right derived functors in the afternoon. So tensor and pullback are left exact. And so we'll do this in the afternoon session. Thank you. And we'll also talk about compatibilities. The pullback of the tensor product is the tensor product of the pullbacks and all that kind of thing we'll do in the afternoon. So I say that we have enough injectives so we can talk about the derived functors, but we want to compose them. Right, so what if we want to compose? So if I have f from x to y and g from y to z, we know that g lower star after f lower star is g after f lower star. And we would like to say that rg lower star after rf lower star is r g after f lower star. That's what we'd like to say. By the way, if you only learn one thing from this summer school, learn to read that little circle as after. It'll sort you out. And you see, already we have a lot of composed things here, right? Like, there are a lot of other compositions, like right there, global sections of sheaf Hom is straight Hom. We'd like to have all that work the way we want it to. And then next time, in the next hour, Sasha will talk about how to take a statement like this and get a spectral sequence that, in this case, it's the Leray spectral sequence that really helps you compute. So what's the issue? I'll write it here. The issue is that F star doesn't take injectives to injectives. Right? So how did we define, how did the derived functor go? We had the derived we had this. How did we get derived functors from here to here to here? Well, in here you had the homotopy category of injective quasi-coherent sheaves on X, and this mapped here, and it was an isomorphism. And so we chose an inverse, and then we just applied F lower star to get to take our complex of injective sheaves to a complex of sheaves. And so this composition was RF lower star. Chose an injective resolution and hit it with F lower star. And similarly here, if I do RG lower star now, right, then I choose an inverse like this, and I apply G star, and that gives me RG star. But of course, that's different. Where'd my red chalk get to? There's no reason to think that agrees with R G after F star would be gotten by doing this and then G after F star, which is G star after F star. But this middle step here is going to give you a hard time. So we need to do something looser than just injective resolutions are maybe asking too much. And the solution is going to be flask sheaves, which are, it's a bigger class than injective sheaves. Questions so far? So definition, a sheaf F is flask or flabby. Flabby sounds a little too silly, but it is a literal translation of the French word. If whenever you have an open set in another open set, F of U surjects onto F of V. So, right, in other words, if here's U and there's V, and I have a section of my sheaf over V, every section on V extends to U. So this is a very ungeometric condition, right? If you were talking about a sheaf of continuous functions or algebraic functions or whatever, your function could absolutely blow up at the edge of V, and then it just wouldn't extend to U. So whereas the sheaf of discontinuous functions on a space does have this property. Where's my eraser? Oh, here it is. Right, so maybe a proposition that I won't prove any of because it's all in Hartshorne. First of all, injective sheaves are flask. So this is Hartshorne lemma. Oh, I've looked it up. 3.2.4. So if you want to go read this kind of thing. 2, if F is flask, then the higher cohomology of F vanishes. It could have global sections, but it doesn't have any higher cohomology. So from the point of view of cohomology, it's as good as an injective sheaf. I'm going to call this gamma acyclic. And I'll define for you acyclic with respect to any functor in just a minute. If you want to work hard, so exercise, which is hard. So think about a check proof. Right, so the proof in Hartshorne 3.2.5 goes through injective resolutions and is very algebraic, but you can also do cohomology there's a check definition of cohomology, and it's fun and hard to think about why flask sheaves have no cohomology in the check picture. And then 3, the push forward takes flask sheaves to flask sheaves. And so this is also, let's make this an exercise. This one is easy. And so the idea will be, instead of replacing, instead of defining the derived functor of f star by taking an injective resolution, let's be happy to take a flask resolution, and then we can really compose the things the way we want to. So, and how does this look more generally in terms of other functors? So definition, given a functor, functor between two abelian categories, an object, maybe I'll call it little a, in A, is f acyclic, if the derived let's say that A has enough injectives. Given a left exact functor like this, if Ri f of A is 0 for all I bigger than 0. So to compute Rf of anything, it's enough to resolve it by acyclic sheaves. It doesn't have to be acyclic objects. It doesn't have to be injective objects. Injective objects are acyclic for every functor, but if you have some more acyclics hanging around, you're welcome to use them. And the next definition I want to make, a class of objects in A is adapted to F if, first of all, it's closed under direct stums. Two, all the objects are acyclic. So every object is F acyclic. And third, every object in A can be embedded in an object of the adapted class. So Flask sheaves are an adapted class for push forward. But later, we'll be doing some of these left-derived functors, like the derived functor of pullback, and there we won't have enough projectives around, but we will have enough locally free sheaves, and those will be an adapted class for pullback. So we're gonna use this. So the proposition given left exact functors f, well, let's have f go from A to B and g go from B to C. These are between abelian categories. Let's say suppose there exists an F-adapted class RA and a G-adapted class RB in B, such that F takes the first adapted class into the second adapted class. Then the right derived functor of G composed with F is naturally isomorphic to the right derived functor of G composed with the right derived functor of F. Right? So in order to, this diagram that's still sitting up there, you can imagine it with A, B, C, and F and G. The point is we don't want to change resolutions midstream. Right? We're not so rigid that we require that we require an injective resolution to define RG. We're happy to take a resolution by Flask sheaves or objects in that adapted class. But the point is, F really takes this class into that class, and so we can go all at once without re-resolving in the middle. By the way, notice maybe I'll say it in words first. What did we do? We had this nice adapted class, injective sheaves. We added some more Flask sheaves. Why not just add in everything that's acyclic for push forward, right? While we're adding more things, why not do that? So notice that if you have an adapted class, RA, you could throw in all F acyclic sheaves or objects. to get a bigger one. Right, it'll still be closed under sums. It'll still consist of FA cyclics. If you could embed every A into, before we could embed every sheaf into an injective sheaf, so we can certainly embed every sheaf into a flask sheaf. But this would be this is in tension with F of RA being contained in RB. Right, so you might say, why not just make that first class as big as possible, but then we might not be able to make that second class big enough. So there's sort of there's a Goldilocks issue there. So exercise. Find two maps of sheaves, right? Two maps of schemes, like this, and a sheaf F on X that is F lower star acyclic, but F lower star F is not G lower star acyclic. Again, the point is when we go to define derived functors, we didn't have to be so uptight as to use injective sheaves. We could use any old F star acyclic sheaves and we could compute just fine. And maybe we have a lot of those around and we know a lot about them compared to injective sheaves. On the other hand, if you want to do this formal thing about composition, you have to be, you can't just go crazy. In general, there's a huge gap in this subject between how you actually compute and how you set up the formalities, right? Okay, so next, I want to talk about the derived functors of sheaf Hom from E blah, which goes from quasi-coherent sheaves on X to itself. And this will be different because it has two different spots you can plug things into. Right, so we have, time's okay. We have enough injectives. So we get R sheaf Hom from D plus of Q co to itself. Right? I should say, let me be more clear. This is R sheaf Hom E blah. Like this, where E is a sheaf. E is not yet a complex. But now we can take sheaf Hom from E to a complex. By the way, maybe I'll just pause for 1 second. If we look at this thing at the top of the board, why do we want to be in the derived category? Why do we want to take, RF lower star of complexes rather than just sheaves? In Hartshorne, you have a sheaf, you have the derived push forwards of it, which is a sequence of sheaves. That seems all right, right? So why would you need to push forward a complex? And one answer you could give is to say that if I'm going to start composing these functors over and over, so far we have 2 of them, but soon it'll be 3. Your first sheaf turns into a bunch of sheaves, which is really we should think of as a complex. And then you hit that with a functor, and now something new happens. And the bookkeeping could really quickly get awful if you only think about RIF rather than the whole complex RF. So this statement up here, as Sasha will explore next time, when you try to think about it in terms of individual sheaves, there's some big spectral sequence. It's not so clean. And if you have 3 functors, then you really don't want to think about the spectral sequence. So that's I guess the reason we don't build the derived category to take one derived functor. It's so that we can compose derived functors. I should be here, shouldn't I? So great. So we can derive that functor that way. But we could also locally free sheaves are acyclic for the right exact functor. Oh, wait. Well, for the functor sheaf Hom into something. Right? Locally, we're just looking at Hom on rings, and so locally frees are, on a ring, a free object is projective, and that's great. So we can compute R Hom from E dot to F using a locally free resolution of E. And then you have some exercises. Oh, sorry, this should have been a sheaf Hom. Exercise is to compute some sheaf X. I haven't passed around the handout. Here. You have that go around. And it also asks you to compute some tors, which you'll meet this afternoon, but it's the same process, so why not do it? So are there enough locally frees? I guess I should address that. Because I guess I'll say in a second, in the category of sheaves, there are enough injectives, but there are pretty much never enough projectives, unless X was affine. If X is an affine scheme, then of course sheaves are the same as modules, and there are tons of projectives, tons of frees. If X is a projective, this is ironic. If X is a projective scheme, then there are rarely enough. There are never enough projective sheaves, which is such a strange. You never say projective sheaf because they don't exist. So it sounds really funny. In particular, vector bundles, locally free sheaves, are not projective, as we'll see in a minute, but we have enough of them, and they're good for a lot of what we want to do. So let's start with this. So proposition, if X is projective, let's say over a field, then the category of coherent sheaves on X has enough locally frees. So that means that every sheaf, every coherent sheaf is a quotient of a vector bundle. So the reason you have some ample line bundle, so given F, there's some number that's much bigger than 0, such that F twisted by n is generated by global sections. So a global section, so let's say that the thing has big N global sections. So a global section is the same as a map from OX to F twisted by N. And we have lots of them. So we have our N global sections give us a map like that. And to say that it generates that sheaf is to say that this map is surjective. So if you haven't thought about this before, you want to sit and think about whatever definition of being generated by global sections you know, and understand why that's the same as saying that you have a surjection like that. And thus, if I take that thing and I just tensor it, I'm just going to tensor it with O of minus n. And so I have OX of minus n to the n surjecting onto F. And this is locally free. It's a vector bundle. And so exercise, you should think about quasi-projective varieties and or quasi-coherent sheaves. Handwriting's going to hell. So it's spoiler, it's still true. But you should think about what goes into that. Or if this made you uncomfortable, you should spend some time and become comfortable with it. And so every and so because every sheaf is a quotient of a locally free sheaf, so every bounded below complex of coherent sheaves is quasi-isomorphic to a bounded below complex of locally free sheaves, of vector bundles. Vector bundle is a locally free sheaf of finite rank. And actually, we can do a little bit better. We haven't started talking about boundedness very much, but let me say it here. If X is a regular local ring, in particular if it's smooth over a field, or not a regular local ring. If X is a regular scheme, so all its local rings are regular local rings, and if you want, you can just think smooth over a field. That's good enough for our purposes. So if X is regular, in fact, I can just say bounded above and below. Oh, sorry, did I say? I said bounded below when I meant bounded above. I'm sorry. You know, D minus is bounded above because it runs off in the minus direction. Sorry. But if X is regular, I can resolve a bounded complex of coherent sheaves by a bounded complex of vector bundles. So let me say a word about that. And the reason is the Hilbert-Syzygy theorem. So for one sheaf, it goes like this. If I have a sheaf, so let F be a sheaf, and EI be vector bundles. If I have a resolution like this, and I get to the nth step, where n is going to be the dimension of my space, so I might be off by one. Let me just think for 1 second. So if I start making my locally free resolution of my arbitrary sheaf, and then after n steps I take the kernel, then this is locally free. Right, so whatever, you sort of can't make a resolution that you start making a resolution and at some point you can just stop on a regular local ring. On a singular scheme, it doesn't work that way. So in the exercises, look out for a counterexample when X is singular. So on a singular scheme, you might need infinite resolutions by vector bundles. I don't want to prove the Hilbert-Syzygy theorem, but how many have seen it somewhere once in their life? Half? Hilbert proves it for polynomial rings, but it's equally good for any regular local ring. Yeah, we need finitely generated things, I think. Am I wrong about that? No? Yeah, I wouldn't like to say off the top of my head. Yeah, I'm not sure. Right. So this other remark that I wanted to make, the categories of sheaves rarely have projective objects. So unless X is affine. So for example, suppose F is a coherent sheaf on P1. And I'm going to show that it can't be a projective object in that category. And then we know for some n really big, global sections of F twisted by n are not zero. Well, let's say it is non-zero. So if I have a coherent sheaf on P1 and I twist it up really high, eventually it will have some global sections. But global sections of F twisted by n, this is HOM from OP1 to F twisted by n. And it's also HOM between OP1 of minus n and F. I can move right. This is, in general, HOM from G tensor G to H tensor E is HOM from G tensor E dual to H. If G and H are sheaves and E is locally free. Right, that's even true of sheaf HOM. There it's even more clear. And then you take global sections of that and you get the statement that I have here. So E is O of n in this case. And by Serre duality, which Sasha is going to cover, I believe tomorrow, yeah. This is X1 on P1 between F and O of minus n minus 2. So you'll meet, if you haven't seen Serre duality, you'll see it soon. And so, dual vector space. So F is not projective. The nicest non-affine scheme that you can imagine, P1, category of coherent sheaves, doesn't have any projective objects because everything has HOMs from a very negative line bundle and thus X's to a very negative line bundle. You remember a projective object, there would be no X's from it to anything. So if you want, you can think about quasi-coherent sheaves on P1. Let's see how it goes. Oh, I didn't want to do that, sorry. Another more serious, well, another exercise is that, we talked, when we went to compose two push forwards, we talked a lot about taking injectives to flasks and flasks to flasks. So if we want to compose sheaf HOM with global sections to get straight HOM, sheaf HOM from E to whatever takes injectives to flasks. And thus, we can say that from the statement that straight HOM from E to whatever is sections of sheaf HOM from E to whatever, we get R HOM from E to whatever is R gamma of R sheaf HOM E to whatever. Right. So this is the exercise right there. And then this next thing just follows the same way it did for push forwards. If this all seems very dry, in the exercises there are sort of geometric examples, which I invite you, and feel free to read through the exercises and do the ones you like best first. Don't feel like you have to do the very dry ones first. Did everyone get an exercise sheet as they're going around? Who's missing? You guys are missing? Are we out of? Oh. Sasha, can you run off another dozen of these? Okay. So now in the 5 minutes that remain, I want to talk about two things. What about R HOM from a complex to another complex, where they're both complexes? Right, we talked about HOM from a sheaf to a complex. Sorry, let me put R sheaf HOM there. From a sheaf to a complex by resolving this one with injectives, or from a complex to a sheaf by resolving this one with locally freeze. But can they both be complexes? And the issue is that this is not the derived functor of anything from an abelian category to an abelian category, right? Sheaf HOM from E dot to whatever, where E is, it needs to be bounded above. This is not a functor from quasi-coherent sheaves to quasi-coherent sheaves, but instead it goes from the category of bounded above complexes of quasi-coherent sheaves to itself. Okay, yes. right? So it's not the derived functor of a functor between abelian categories, but between homotopy categories, which is slightly grosser, but it's in the end, it's no more trouble. So the lemma that you need to define R hom E dot blah from D plus of Q co X to itself. Right, and the way you're going to do it is you're going to resolve everything by a complex of injectives. Right, this was an isomorphism. So if I want to get that, and then choose an inverse like that, and then do R hom, or just do hom E blah. Right, so what's the lemma that we need is if E or F is acyclic, so quasi-isomorphic to 0, right? No cohomology. No, yeah. And F is a complex of injectives, then hom from E dot to F dot is acyclic. I'm not going to prove that in 1 minute. I'm not sure I want to prove it at all. Maybe I should say something out. What does hom between two complexes mean? Maybe we can touch on this later or when we do tensor products. But you can imagine it's you take the hom between the individual terms, and that gives you some big bicomplex, and then you flatten it out and take all these d's with different signs to make something that where d squared is 0. Maybe we can touch on that later. Same thing with the tensor product. I was going to say something about boundedness, but I think I better save it for the afternoon. So maybe we'll stop there. And Sasha has more exercises for those of you who want them.